So something Dr. Stevens, I like his stuff. One thing I think he could do a little bit more emphasis on in this section is the empirical rule here. He doesn't really mention it other than this. He never really asks you to apply it. Um, but this is true for any distribution that's normally distributed. It'll be close. I mean, if you small data set, it won't be perfect, but it'll be darn close. As you get to bigger data sets, it really approaches these theoretical values. And so what he goes on, where he goes into this, and what he wants you to think about, and what I want you to think about with this, is this: if we have a symmetric distribution, a normal distribution here, let me go to red ink. If we have a result that's more than 2 standard deviations away from the mean, see, 95% of the distribution is there, so there's only a 5% chance it'll be outside of that, which means there's only a 2.5% chance that the mean is truly here and the distribution is normal. Um, there's only a 2.5% chance it'll be more than 2 standard deviations away from the mean in either direction. Okay, so that's what he goes to when he starts talking about outlier tests. He starts talking about how if you're outside that range, it's an unusual result. And this he does this later on in here. Let me get rid of this other stuff that I wrote. You know, if it's more than two, if a result has a z-score that's more than +2 or less than -2, that's unusual. That's not likely to happen if the given mean's true. Um, so let's look at what you wrote for the heights. This is women's heights. Yeah, this is the one about U.S. women's heights. Yeah. So do you see how? So we know that we're told a mean of 64, and if we go 2 standard deviations above or below the mean, let's see, what is the standard deviation? 2.8. So 2.8 times 2 is 5.6. So 69.8 or 61.2. Can I do that in my head? Let's see, 61.2. Let's think about this. If I add 2.8, what do I get? I get 1 caret, right? So those are the cutoffs for unusual heights, and you don't have to spell it out this way, where I'm adding 2 standard deviations plus 2 standard deviations, subtracting 2 standard deviations. We get this great tool in z-scores. And see how that's a z-score 2.14? Well, that's more. Here, let me go to different color ink. Here's my 2 standard deviation mark. So z-score 2, that's out here. And this is out in that tail area. So this is an unusual result. This is an outlier. Having a woman that's 70 inches tall, if this mean of 64 inches tall is true, she'd be unusually high compared to the rest of the female population. And this person that's 67 or 57.8 inches tall, that's below the 2 standard deviation mark. So this person could be considered unusually short for the typical woman's population. How many? What is that? 5 feet. 5 feet is 60 inches. So yeah, they're what? 4 foot. I could do the arithmetic. Let's see. That's three. That's uh let's see, what's 5 times 12? Oh, 5 times 12 is 60. So this is okay. So 4 foot would be 48. So this would be a little more than what? 4'11? 4 foot 11, a little more than that. Maybe I'm doing that math wrong. Forgive me if I am. But kind of gives you a perspective of what they're doing. So calculate the z-scores. If your z-scores are more than 2 or less than -2, you get an unusual result there. An outlier, so to speak, okay? And this is for normal distributions. If your distribution is not normal, we need to use that 1.5 IQR test. That's the other thing. I'll point out some more of that next week when we look at chapter 3.